This is the last talk, right?
Yeah.
So let's wait.
Today.
Yeah, let's wait a minute.
So my problem is I have to leave for 20 minutes immediately at exactly at noon my time, which is 6
Yes.
p.m.
Okay. Let me start.
Let's start.
I start. Okay. Yes. I'm going to talk about the modified Palm version. Wait a minute. Okay, I can see my screen now. The so-called Palm version of a stationary random measure, xi, is an important tool in probability theory, as some of you know. It is, however, not well known that there are two versions of Palm. There are two Palm versions. They are related but different. And for lack of better terms, I will call the well-known one standard and the less-known version modified. The standard version is often given the interpretation of the modified one, and that can lead to mistakes. I'm going to spend at least 10 minutes, maybe 15 of my time on a very trivial case to make absolutely sure what the difference is between these versions. And also, for those who are not familiar with Palm theory, also explaining in the process what it is about, Yes, actually, why is it Palm with a capital P? Well, it's because a guy named Conny Palm, around 1940, he was working at the Ericsson, at the telephone company, Swedish telephone company. And there is a mathematician or engineer, and he noticed that if you took averages in real time, you did get of times between calls, then you did get something different from what you got when you took averages at the event times, at the time of phone calls. And that's the waiting time paradox, really. But he worked out how to go between those two versions. A stationary point process is where what he started with. Well, it's actually more general than stationary theory, but I'm going to concentrate on the stationary theory. So he, yes, he devised a way to find out what would be seen from event at the time from the times of phone calls, and that has been called Palm version. I call it here standard Palm version, the standard way of doing it. But actually what Conny Palm was after is what I call, or is called sometimes, the modified Palm version. They are not always the same, even if they are often the same. So I'm going to explain these concepts through their interpretations, not through the definition of the general Palm version, but through the interpretations to start with. And I will look at coin tosses for at least 10 minutes or even more. Sorry for that. Okay, so we have a two-sided sequence of i.i.d. coin tosses here. And here is, they are enumerated. Here is the coin toss at 0, and the next one at 1, plus 1, and here is the one just before 0. And the interpretation of the standard Palm version is that there happens to be a head at the origin. So here, there happens to be a head like this. And this is really conditioning. It's conditioned on a head at the origin. The modified one comes this in this way. The interpretation of the modified palm version is that the origin is shifted to a typical head, chosen at random in a huge window. So you see, we take, we are up here in the stationary sequence, and we take the origin and shift it to a randomly chosen H. So I chose this one, and here is a lot of things going on in between because we are in a huge window. And that is a typical head. And what we see from this head is going to be i.i.d. coin tosses in both directions. So it's exactly the same thing as we see from here. I'm now going to look at a case where this is not, we don't get the same thing. So here is a preparation for next slide. Let P be the probability of a head. So the coin could be biased. And write psi P of the set A is the number of heads in the set A. So psi P is a Bernoulli point process. For example, if there is a head at the origin, then this is the way to write it in this notation. Okay, so now I'm going to have two coins with different, one with probability P and the other one with probability Q. And I randomize which coin I use. So M is a random variable with values P and Q and independent of the coin tosses, with the P coin tosses and the Q coin tosses. So I choose a coin at the beginning and throw the other coin away and don't use it at all. Then you see that sorry?
Your M is just a random environment. You choose an environment, M, and then use it.
It's a random variable with so we have two coins lying on the table and we randomize which one we use. So it's a random variable. I'm just picking one, throwing the other one away. And okay, so in this way we destroy the independence between the tosses. But we keep the stationarity of the sequence. And I will use psi for the choice of the coin tosses. Okay, so here is the probability of a head at the origin. So it's very simple. We just take the expectation of M like that. Okay, and then let me go on. I will use this for this strange symbol up there to say indicate the point process where we don't, where we exclude what happens at 0. So it's all the other coin tosses. Then if we look at what happens outside 0 and say there is a head at 0 and that M is P, then we can replace this by this and this by this. And though everything is independent here now, so we get this. And if we divide this by this, the probability of a head, we get the conditional distribution of the coin tosses outside. M equal to P, it is this. It's just, now it's just independent P coins outside 0. And here, what do we get here? We get, what do we get? Okay, anyway. Strange. we get a size-biased version of M. So given a head at the origin, what is outside the origin behaves as these two coin tosses pre-mixed by a size-biased M. So the probability of M being P given a head at the origin is this, which this was a long way argument for a simple thing. But the interesting thing, it's a size bias thing that's going on by this conditioning on the head of the origin. Now let's look at what happens when we shift to a typical head and do not do this conditioning thing. So this is what we had, and recall the size biasing when we condition. And now look at Xi from a typical one, from a typical head, shift the origin to a random head. Then conditionally on M being P, if we happen to have the P coin, we would see i.i.d. coin tosses with probability P or intensity P. Thus, outside the new origin, we would see coins behaving as the two coin tosses pre-mixed by the original unbiased M. So when I'm going to give you the general definition of palm versions in a minute, but they turn out, the two palm versions turn out to be such that the standard palm behaves like our Xi, conditioned on the head at the origin, while the modified palm behaves like our Xi, seen from a typical head. And as you have seen, we are not getting the same thing out of this. And it's because palm theory is done in a stationary context, is often used to find a typical event in a stationary sequence of events. Can be important observation, that we should use the modified one in that case.
It is important because I have used it in several applications. That's it.
Yeah. So I'm just, I know, because lots of people, I'm not talking about you, Takis, lots of people think you get a typical head, typical event by conditioning on an event at 0. Anyway, let's go on now. The definition of the palm versions in a general stationary setting, and I'm sorry, it took 15 minutes, that's what I sort of expected. The general stationary setting that I'm considering is very different from the coin thing, even if the coin setting is a special case of that. So I have a general probability space supporting all random elements below, and G is a locally compact second countable topological group with the Borel sets G, so it's a very general setting, and left invariant Haar measure lambda. And let Xi be a random measure on G, and in our example, G is simply the integers, and Xi is the coin tosses. And then now I'm going to introduce an external thing, a new thing. In addition to the point process, there can be some X present, which is a random element in a space on which G acts. For example, X could be another random measure, or it could even be Xi itself. And then it's unnecessary to introduce it. Or it could be a random field indexed by the group. Write theta t for the shift map placing a new origin at t in G. For example, if G is the real line, then theta t Xi of the theta t of the random measure psi is defined this way. This is moving the origin to t. And if we have a random field, we are here moving the origin to t. Also, the joint shift is defined by this. This joint shift of x and psi is just this. And throughout, let psi, x psi be stationary. So the shifted x psi has the same distribution as the original x psi. And let p be the stationary distribution. That is just the distribution of the pair. This is the setting, and now the palm versions. The palm versions of a stationary pair. This pair is a random element in some measurable space. I will denote it by H for Hermann. I just picked some letter I'm not using. And then something called the palm measure. I don't know if Palm ever introduced a palm measure, but this palm theory went through a long trip through Eastern Germany and through the head of Olof Kallenberg and wherever, into applied probability everywhere. And this is not a palm phrase, but it's something that is in standard palm theory. So what is the palm measure? Well, we take a set in this H. The palm measure, so the palm measure is a measure on this space. So what we are doing, we are shifting the pair x psi by s and integrating with respect to the random measure over some set b and dividing by the mass of B, the Haar mass of B, or the Lebesgue mass of B if we are in that situation, where B is arbitrary. It doesn't matter what B it is as long as this holds. So what does this do? It sort of stresses locations S with much mass. And where there is no mass, this doesn't show up. So it is moving the emphasis of yes. So it is sort of smearing, choosing a location according to the mass somehow. And so we take the expectation of this, and the total mass of this measure is the intensity of psi. You can see that by, if we put in the whole H here, we get 1 here, so the integral of B is just psi B, and then we divide by the volume of B, or the lambda of B, and then we get the intensity. If the intensity is finite, we can divide by the C and get the standard Palm distribution this way. So now we have in that case, we have a probability measure. And now to the modified Palm, we need the invariant sigma algebra on H, on this space here. It's all sets that don't change when shifted. And then I use J, script J, for the invariant sigma algebra of X and Psi down in the underlying probability space. And now use capital C to define a conditional intensity divide. So we take what is this? It's the conditional intensity of psi given the invariant sigma algebra of the pair. and then we divide by lambda b, and we get something called sample intensity, and it's a random variable. And if that random variable is finite almost surely, we define the modified palm in this way. So it is similar to this definition here. When we divide here by this little c, we can do it inside, and here we divide by capital C instead. And I'm using this notation that this is the standard pair, palm pair, it's a pair with a distribution, with standard palm distribution, and this is the pair with the standard, the modified palm version, the modified palm distribution. Okay, so I'm going to focus on the modified one because I'm going to show, show you a theorem saying that this modified version is really what describes the original stationary thing seen from a typical location in the mass of psi. Okay, so here is that theorem, and I'm skipping the proof, and if you would like to see some of it, I have it after this slide, or maybe we do something else. But let me go through what comes out of this. So we need sets that are Fellner. Fellner sets have the property, they are sets in the subsets of measurable subsets of the group that indexed by some R, that they set expand to the full group. It's like a ball, B is borel or ball. It's like in d-dimensional space, we could have a ball, open ball containing the origin, and then blow it up by multiplying by some R, and then it expands to the full space, RD. And so keep that example in mind. So the sets are Fellner if they expand to G, and if for all locations the volume of the set B, and this is here is the set B, and here is the shifted set B, and this means the symmetric difference. So it's everything that's in the two sets, but not in the intersection. So the condition is that the volume of what is not in the intersection divided by the total volume of the ball goes to 0. So the the BR and the shifted BR become basically the same in the limit, volume-wise. And here is the theorem. So here is a stationary pair, and this is the modified palm. And suppose there exists Fellner sets, and I could mention that the balls I talked about are Fellner sets, and it's a much more general thing we would get if we take bounded convex sets, open sets with containing the origin, and blow them up. They are also Fellner. And here comes a terrible restriction. I am forced to assume that the group is abelian. I would like to get rid of it. I don't know how. I don't know. Maybe it's not even true then. Let's see what the statement is here. Okay, so we take the pair, the stationary pair, and we move the origin to a random location that I denote this way, S, indexed by the ball, where this random site is chosen according to the mass distribution in the set B. So the distribution of this location given both x and xi is the mass restricted, conditional mass on that of psi on the set B. So it's choosing a mass location, a location in the group according to the mass distribution on B. Okay, and if you then blow up the B's, we get in total variation the modified pair in the limit. So this motivates the interpretation that the modified version behaves like the stationary one seen from a typical location in the mass. So what do I have? I'm basically finished with my time. There is supposed to be time for discussion, but I'm going to show you that the key steps of proof, they are shift coupling and mass stationarity, two concepts that are not too well known. So here is a fast proof of the theorem. Shift coupling is here, just show you the slides, and then shift coupling applied to the Palm version. So this is the result of the shift coupling theory, that there exists a random location in G such that if we shift the origin to that location, the modified pair has the same distribution as the stationary pair. So the stationary pair can be found in the modified pair by a certain randomization, which can be, it's here allowed to extend the underlying probability space. And from this, this limit theorem follows. And this is different from the one that we had on the slide earlier. Here we take the modified version, and U is uniform. It's distributed according to the harm measure on BR, independent of the modified pair. So we are just picking a uniform. We are just picking a location at random in BR and shifting the origin of the modified one there, and then it goes in total variation to the stationary pair. This is without any restriction. It's not necessarily, we need not assume that we have an abelian group here. So it is a pity that the other theorem need that. But let me now skim forward. So here is mass stationarity. I'm not going to explain what it is, but it has the following. It is a characterization of Palm versions, both the standard one and the modified one. Mass stationarity means actually that the origin of the pair is at a typical location in the mass of the random measure. Okay, and here is the theorem I had. Now we are shifting in the to a location according to the mass distribution, and then the stationary one tends in total variation to the modified one, and we need abelian for that. And here is the proof, and I'm not going to go through the proof because you don't know what mass stationarity really is, and or shift coupling, but I'm going to stress where the abelian assumption comes in. It comes in this line. If you see here, we shift to the S, it's like this. Here we don't shift. Here we shift to S as we did there. But here we shift a lot. We shift a lot. So we are actually, the first shift is up here. It's, yeah, I can tell you this XM is the modified guy. And here we take the modified guy and shift it to a typical location in the set according to the mass in the set BR. And by that, the distribution doesn't change. So we can replace this by that. And then I put in U, the inverse of U here and U here. And that's just a rewriting of V. And then on the next slide, I'll show that this gives us, we have now this, by this, we can turn this proof, this equation into the one on the slide before. On this one, we can apply this result, but we need to have an abelian group for that, because that's the way to rewrite this V in this way. Couldn't do it in general. Okay, and here is the end of the proof, and then here is a reference, only one, and there is it's a lot of references in that paper. It has a historical section at the end.